Hi, my name is Tianyi, and this is my group member Yu. Our project of ECE661 is GPU performance optimization with local cache share and frequency scaling. So here's our introduction. Basically, our motivation is that in GPU, the L1VD, which is the vector data cache hit rate, is relatively low inside the GPU. So most of the benchmark shows that L1 has less than 20% hit rate when compared to most of the CPU caches. So this low hit rate of L1 vector data cache results in a high contention of the memory access in L2 caches, which makes the L2 becomes a performance bottleneck for GPU. So if we can optimize the L1 vector data cache, our GPU will be able to benefit more from the current L1 cache size without changing, like making larger, which makes more makes it more costful, and the high contention of L2 can be reduced. So in our paper, we contribute the following 3 points. We first combine the private L1 vector data cache for each of the compute units into one by a factor of 4. So basically, each 4 of the compute unit will share one L1 data cache. The point of doing that is that the workgroup locality, the memory coalescing, will be improved by doing that, which results in improving the L1 vector data hit rate. Basically, now your 4 of your compute unit will be able to reuse some of the data if it's shared with each other. And the behavior of L2 cache has not been mentioned too much in the existing model we used. So we actually researched on the performance impact of different L2 cache size, and we found that sometimes the smaller L2 can even result in better performance. And we also add some frequency scaling technology, which we found that it has positive impact on further optimizing the target GPU architecture performance. All of these we'll go into details later. So in basically our proposed architecture is each of the 4 compute unit is connected to one shared L1 vector data cache. So in the picture here, as you can see, it's connected to 1 instead of before they only have their private ones. So our associativity and block size is multiplied by 2 at this point, because you want 4 times the cache size. So according to this equation, we increase the block size associativity by 2 each other, so you have 4. And because you're now having 4 of them connecting, you will require more connection. So for example, your coalescing unit, which helps you to merge the same cache line data together, it will require more ports so that it will be able to connect more frequently with a larger amount of data with each of the 4 compute unit. So we already seen the structure here. As I mentioned again, you just like having all these 4 connect here compared to here, and these are the general structure. Here you have the switch controlling the L1 and the L2 here, and it will be able to switch between the interconnection network, which we call the control flow. We didn't look too much into it, but these are the further studies we can be doing. So next part will be the frequency scaling, and some of the simulation results will be introduced by my group member Yu, and he basically ran the simulations and did the frequency scaling.
Hi, I'm Yu. I'm going to talk about our proposed cache size related GPU frequency scaling. And here you can see in the picture the variation of the frequency of GPU it's not the common sense that similar to the CPU DVFS, which is the higher frequency means the high performance, but in GPU the high frequency will not sometimes will not increase the performance. So we can see here the variation of the frequency against the performance is not predictable. So the impact of the change are not predictable. So we propose our cache access related GPU frequency scaling. So here's the basic algorithm for our schemes. You can see in the picture here. We basically calculate run the applications for each frequency and calculate the miss rate of the two types of level 1 cache, which is the vector cache and the scalar cache. We can see here, and then we divide the each type of the cache miss rate, by the number of the scalar instruction and the number of vectors instructions. So basically here we introduce our algorithm to deal with the impact of varying frequency. So when the frequency changes, we will be recording the M value and made a comparison with the different M value, and basically the higher the M value is, the better the performance is. So the basic idea here is to analyze the L1 cache miss based on two types of instruction, which is the vector instruction and the scalar instruction, and decide the best frequency case. So let's jump into the experimental setup. So we use the multi-2-sim simulator, and we run our benchmark based on the AMD official AMD SDK, and our architecture is based on the Thousand Island AMD architecture. So here we can see our cache configuration. In the table, let's first look at the level 1 vector data cache. So we basically combine 4 of the original baseline cache into one large cache. So the total size of the two configuration of level 1 vector data cache is the same, and we simply increase the level 1 scalar data cache by 2. So we will get some improvement. And for the level 2 cache, so to fulfill the requirement of increasing level 1 cache, we have to meet the level 1 basically the level 2 basic baseline configuration. So we can see here. Here is our experiment result. For first come the different level 2 cache. So let's look at the up here, the top figure. It shows the comparison with the baseline and our modified configuration. So this one is based on 4 times original size of the level 2 cache, and we can see our proposed optimized level 2 cache size, which has actually smaller than the 4 times original level 2 cache, but it get the similar result and a similar performance improvement. And even though and we get even more improvements on some of the application. You can see the multiplication here and the for visual. So let's jump into our so we actually pick up 4 representative applications to illustrate our improvement on the miss rate and the level 1 cache miss rate. So with 4 representative application, you can see the significantly increase on the radix sort here. The level 1 vector the data cache hit rate is increased by about 4 times, even more than 4 times. And for the CGFS analysis result, We can see from the figure here, the trend is close, but not accurate. We can see the narrow line of in the picture is our M value, and the thinner is the performance. So the limitation of the simulation results statistics and possible compelling issue will create this singularity point, I think. And but the overall trend of the analysis is close to the best frequency case. So we can see their trend is close. So we may first improve it by studying the details frequency impact and the reason why this would happen. And I will introduce my friend to cover the conclusion part.
So first, basically in this study, we studied the cache behavior and modified the existing GPU cache architecture. So if you read the paper, we actually found we first studied the behavior and found that L1 has this very low hit rate. So we did the research and found this paper so that we can combine the L1 data cache together for a better hit rate. And we examined their model, and it turns out it works out. But we have trying to be improving and figuring out what they didn't do and trying to make it better. So we introduced this cache-related algorithm, and we analyzed the impact of frequency scaling, because we thought that higher frequency is expected to give you a better performance because you're running more circles every second. But it turns out it didn't do that, and only a specific setting of the frequency will be resulting in the best performance. That's why we have this algorithm, and here we combine them together so that our actual performance was improved by at least 20% compared to the original work. But some of the future work, which is exactly what we didn't do, is we didn't study too much of L2 and the main memory architecture optimization. We just did a little bit on L2, as you can see. L2 cache didn't affect too much. From my understanding is that because most of your data is in L1, your hit rate is becoming higher, so that you don't even need to access L2. And we don't really understand why the frequency is varied for the cases we tested, especially the benchmark. It might be related to some of the interconnection and maybe wavefront or other kind of control flow issues. And energy is the thing we didn't look at because it turns out when we did the research online, most of the people, when they do research, they have the actual GPU and they tested the energy consumed on the GPU. And there is not really a good model of GPU on our simulator. There is something called, what's that called? MacPack?
Yeah.
MacPack. It can be used, but we just don't have enough time to integrate it into our simulator. But that's definitely something we can do in the future. That's it. Thank you.